Hey everybody, we're Team Hotspot. I'm Avi.
I'm Evan.
I'm Kyle.
All right, so our clients are Nalay Gupta and Shiji Wen from Cisco supply chain team, and they are currently having issues with their router boards. These boards sometimes encounter voltage fluctuations, which can then lead to device failure and then eventually could possibly lead to catastrophic network outages. And since a lot of Cisco's products and services rely on the network, they can't really afford this kind of unreliability in their boards or these failures. And so what they've done is they've asked us to look at these data files, which have a bunch of board voltage sensor data, and to try to find a correlation between those voltage fluctuations and board failures.
So we're using a similar approach that people use to statistical modeling in order to predict device failure. What we're doing is we're starting off with a bunch of experimental data. We're using that to build a statistical model, and then with any given device that we have with board readings, we then use that new information to predict the remaining lifetime of the device.
So we have 9 primary engineering specifications for this project. I'm going to touch on 3 of them. First one I want to touch on is performance. We received thousands of data files from Nalay, and that's a lot of data that we have to parse through. And so making sure that we can handle each file quickly and efficiently is very important. Right now, we are sub 1/10 of a second per file. But as we add more, this is like a maximum 1 second per file. And then accuracy, since we're predicting on behalf of customers, we need to make sure that we're accurate, because we want to say this device will fail confidently, and we want to say this device will not fail confidently. So we want to be able to make 95% accurate predictions, or better than that. And then finally, number of sensors supported. We've found in our files at most 92 voltage sensors on the boards. So we want to make sure that we can take in as much data as possible. So whatever we design, the input has to be able to take at least 92 sensors to accommodate all the data. So we started with our initial prototype. It outlined a service which would take in voltage and temperature data, do some stuff to it, and then decide, is there failure indicated by this voltage data? And if not, when will failure potentially happen? So we take 5 steps. First, we get input data from the user. Then we parse and convert the data to a computer readable format. Then we interpret the data, determine is there failure in this data, and if not, we provide an expected time of failure. So to go about figuring out how we wanted to approach this problem, we conducted a brainstorming session. We categorized the components of our service into 3 parts: parsing, visualization, and analysis. So for the parsing part, we decided on Python for our programming language, and JSON as our computer readable format. So Python makes parsing files really easy, so it's super friendly. Also, Python dictionaries are very similar to JSON, and so right out of the box, we can support JSON files as well as Python dictionaries, which is why JSON is great. For visualization, we considered a couple plotting libraries, Plotly and Matplotlib. While Matplotlib is very widely used, Plotly actually has both a Python binding and a JavaScript binding. So if we wanted to make a web interface for visualizing the voltage plots, we could use Plotly as well. And then for analysis, as Kyle mentioned, some people use statistical models. We were thinking we could also use machine learning. Since we don't really know what a statistical distribution would look like for this data, we've actually decided that we wanted to take the machine learning route. You have a black box, you throw a bunch of data into it, it spits out an output, and that seemed most reasonable for our project. So there were 2 options that we could think of: TensorFlow, which runs on consumer devices, and we could run on your laptop, and then AWS SageMaker, which runs in the AWS cloud. And while SageMaker has a lot of really good models, and you have EC2 compute power, which could like outperform any laptop I could possibly run a model on, we wouldn't run into any security issues if we used TensorFlow, because all the data would be local. Whereas uploading thousands of data files to AWS, S3, whatever, we'd have to make sure that it's secure, no one could access it because it's critical data. And then after all that, we arrived at our final design concept. And this looks very similar to our initial design concept. And that is because what we've discovered as we received more data and more information about this project is that we can just build on our initial prototype. So instead of taking significant direction changes or building out components, we've just been adding features to our initial prototype and building out the functionality that we have to enable us to make better predictions and analyze the data better.
Okay, so now we're gonna kind of run you through what we do with the data file that was provided from our clients. And so here's an example of a data file. And so at the top, there's a lot of header information that we've kind of just been asked to ignore. It's not really necessary for us. And then the boards also have temperature sensors. That data is also pretty useless for us. But then here we actually get to the voltage information, and that's where we start to see the information that we actually want to extract. And then this is going along the same untouched data file. We actually start to see timestamps and voltage values for each of the sensors right here. But then as we reach the bottom of the data file, there's more information that's not really relevant to us, such as power ratings and RAM information. So after our initial parsing, we kind of just only extract the useful information, which again is just voltage data. So after parsing, all we have left from that file that you just saw is a header, the number of sensors, sensor names and IDs, and then timestamps and all of the voltage values for each of the sensors.
So once that parsing is done, we're ready to be able to put it into a more computer-friendly format. And so what you see here is we've got a big dictionary for each file that has all of the timestamps on that file, and the data value for each of those dictionary entries is a list of each of the sensors. And so the sensor name, the sensor numerical ID, and the voltage reading for that timestamp. And so we can go through each of the files, run this code, and then get the voltage fluctuation information. So you can see there's a bunch of different files here. There's a number of small fluctuations, large fluctuations, and the fluctuation rate. A small fluctuation isn't very interesting. It's something that it's only a fluctuation of 10 millivolts or less. And fluctuation is basically just if the voltage reading is different on the current timestamp from the previous timestamp, that's categorized as a fluctuation. So we get the fluctuation rate from just the number of large fluctuations divided by the total number of sensor readings.
And then from those fluctuations, we can start to visualize data. We have, as I said, a lot of files. And so being able to use this rate as well as the number of sensors we have can help us to find things like this. So when you look at this plot, on the right side, you can see all of the sensor names that we have. And then those correspond to each of the traces that you can see here. And this y-axis is the voltage in millivolts, and the x-axis is the time. And so whenever you see a drop like this is generally a voltage drop to 0, and these are interesting. And the other ones you see are these kinds of fluctuations, which look to be around 50 to 100 millivolts, because this is like 1,000 scale. And these are also interesting. And so these two kinds of voltage drops, like these ones, these are all things that we use to label our data set when we start training the model. Because this might indicate failure. And so we want to be able to identify this from the data. So here's what our timeline looks like. This is where we're at. This first quarter, we spent mostly working on parsing and visualization, because if you don't have parsing down, can't really get into a format for a neural network. If you don't have visualization, you can't label your data because it's really painful to look at just JSON. So it's nice to have some kind of plot that allows you to see these fluctuations. And then moving forward in the next quarter, we're going to be mostly working on TensorFlow, training a model, collecting our data, labeling the data, and training it, and cleaning up our code base, and then we'll be at beta. Any questions?
How often are the sensors collecting data?
So it's around 40 minutes per sensor, and then if they notice fluctuations on board, they take more frequent samples. And I'll show that later. You can actually see that on the plot, see like a couple fluctuations, and then the samples get tighter. Yeah.
What do you expect the machine learning aspect of this to discover about the data that you would be able to find out really formal, like statistical analysis?
Yeah, so we want to be able to, so that's a great question. With regards to like statistical distributions, I'm not entirely sure. With a machine learning approach that we're taking, we want to use some kind of regression model, which would allow us to say, you know, this doesn't indicate failure yet. There are no fluctuations, but we have seen, or maybe like small fluctuations, but we've seen these kinds of fluctuations before. And so we think that in the future, you'll see even worse fluctuations and the board will fail, that sort of thing. Does that answer your question?
You have a lot of data sets. You're going to train the model on all of the data sets you have, or then test them on a few, or what's the plan there?
We haven't really thought about that yet. I think that's a very good point. You have different sensors for each of the product lines. They're used differently. They might be in a different space. So I think having separate models would be an interesting thing to consider. But that's something that we have to explore. Any other questions? Thank you very much.